Here we are discussing about a project camouflaged logic gate using threshold voltage defined memory cell. Here the camouflaged logic gate circuits are widely used in secure VLSI applications such as defense electronics, cryptographic processor and intelligent property protections where the resistance to reverse engineering is critical. The threshold voltage based camouflaged technique offers a strong security without altering layout patterns, providing advantages such as invisibility to optical inspections and compatibility with a standard CMOS process. However, the existing approach often suffers from increased power consumptions and larger delay, complex dynamic circuitry and area overhead. In current research, the camouflage gate based on a dynamic threshold voltage logic and threshold defined switch defines have been demonstrated. But this method introduces a dynamic power overhead, leakage issues or degrade performance due to weakly turned on transistors. To address this limitation, this work proposes the development of a camouflage logic gate using threshold voltage defined memory cell implemented in 45 nanometer CMOS technology. It focusing on reduced power consumptions, propagation delay and silicon area while maintaining a strong security against reverse engineering. But this proposed design uses a static CMOS logic combined with a threshold voltage defined memory cells to select intent logic functions and eliminating a dynamic pre-charged operations and also minimizing the leakage current. In addition, the proposed camouflage logic gate is extended to design key sequential circuit and including a data flip-flop and shift register and demonstrating its suitability for practical digital system applications. The novelty of this work lies in integrating a low overhead camouflage logic gate into both combinational and sequential circuit using a scalable 45 nanometer CMOS implementation, and performing evaluations is carried out through schematic design, layout implementations and post layout simulation using Tanner EDA tool, where the parameters such as power consumption, delay, area and leakage current are analyzed and compared with conventional design to validate the effectiveness of the proposed approach. Okay, so now we can verify the paper. So this paper is fully designed for the proposed work implemented as a camouflage logic gate. Okay, so that is the base of the TVD-MC architecture, that is a threshold voltage defined memory cell. Okay, so it will be present in figure 1 architecture. So this is the architectures. Okay, TVD-MC. Okay, it will product the integrated by reverse engineering. Okay, so this TVD-MC is built with cross coupled inverters. Okay, so here M1 and M3 is one inverter and M2 M4 is another inverter. Okay, so it will be stored logic value is determined by automatically during power up by imbalance between a low and a high voltage threshold level. Okay, so it's requiring no additional programming or control signals. Okay, so this stored value is then used to secretly select the actual logic functions among the multiple candidates. Okay, so by using this TVD-MC as a multiplexers, MS-TVDMC architectures, it will be introduced. Okay, that means a multiplexer-select TVD-MC. Okay, so here it will be present in the next figure of figure 6, the proposed MS-TVDMC camouflage logic gate. Okay, so it's a present with a 2 input and a 2 logic gate which using for NAND and NOR. Okay, with the 1 multiplexers. Okay, so this TVD-MC given as a select point. Okay, so here this architectures as a multiplexers will correct the output based on your TVD-MC data and making the true functions indistinguishable from camouflaged logic gate. Okay, to further improvement of this architecture MS-TVDMC, okay, the proposed architectures will be developed in LM-TVDMC. Okay, so it means logic merged TVD-MC architectures. It's integrated with a logic gate and the multiplexers at the threshold transistor level. Okay, so it's enabling a function selections by tuning specific transistors on or off using TVD-MC output. Okay, so because this designs rely on static CMOS logics rather than the dynamic circuit or biased. Okay, so they significantly reduce delay, power consumptions and leakage current while maintaining a strong resistance against the reverse engineering attacks. Okay, so this designs we developed in 45 nanometer CMOS technology using tan IDA tool, and we proved the performance. Okay, additionally the proposed work, it will be designed with the D flip-flop, that is a data flip-flop already implemented in this work. Okay, here this one. Okay, but we used this D flip-flop and we developed a shift register concept. Okay, so here we'll verify this work one by one in a Tanner EDA. Okay, so this is a Tanner EDA. The initial design is a TVD-MC. So this is a design. Okay, so cross coupled inverters. Okay, so here this output we can analyze it. Okay, so input voltage we given 0.8 and the threshold voltage we given for 0.7. Okay, okay, so once executed, okay, so here you can analyze the threshold voltage. Okay, so this is the output voltage level QB and Q. Okay, so after power up, okay, so we'll get some static line. Okay, that is a 0 or 1. Okay, so it will be vary, depends upon your input voltage. Okay, so here we are given as 0.7 voltage. Okay, so as per this architectures, okay, the Q and Q bar, it will be used in a selection line, that is a multiplexer selection line process. Okay, so this is a selection line process, this is a TVD-MC, and this one is a multiplexers, and this one is a NAND and NOR gate architecture. Okay, so this QB it will be used for this multiplexers. This multiplexers, it will be select the which output we need. Okay, so that is a NAND output or NOR output. Okay, so depends upon the input threshold voltage. Okay, so it will detect the NAND and NOR logic gate operations. Okay, so here we will execute this work. Okay, so now we will give as a 0.7 input voltage. Okay, so it will be working on NAND gate operations. Okay, so 0 0 1 0 1 1 1 0 1 and 1 1 means it's 0. Okay, and the next one is LM-TVDMC. Okay, so this is a logic merged TVD-MC architectures. So now we'll execute this. Okay, so this also presents with an AND gate operations. Okay, so that's why this architectures we can use D flip-flops for NAND using architectures. Okay, so this is a LVDMC, NAND using D flip-flop architectures. Okay, so here we solve it. Okay, so this is the D flip-flop method. Okay, clock, data input and data output. Okay, and the next one is a shift register. Okay, so this is a shifting method. So here the 4-bit shift registers we have used in this work. Okay, so here you can analyze the shifting value. Okay, so Q0, Q1 and Q2. Okay, and this comparisons part we can analyze in T-spice. Okay, number of MOSFET and delay measurement, and power we can analyze it in a log file. Okay, okay, so here, and this comparisons updated in a comparisons table. Okay, and we have written abstract document for this project. Title, base paper abstract, improvement, and proposed title, proposed abstract, general notes, existing system, Disadvantages: proposed system. Okay, and VLSI nodes, everything we are at it, and finally come up with literature review, okay, and references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.
Introducing NXFE Innovation, your trusted partner in IP design and VLSI research. With over 300 plus completed projects in cutting-edge domains like low-power VLSI design, high-speed data transmission, signal processing, and secure networking, we offer tailored solutions for students and professionals in BE, BTech, ME, MTech, and PhD programs. At NXFE, you not only get expert-guided projects starting from RIS 6000 Resparus, but also enjoy unmatched benefits like RIS 1000 off on your second project, free documentation, and easy-to-understand video explanations. Plus, our rewarding referral program lets you earn up to RIS 2000 MANTs for every successful referral. Trust us to simplify your research journey with high-quality, affordable, and fully customized VLSI solutions. Visit our website to explore a comprehensive collection of projects, organized year by year from 2014 to 2024. The latest 2024 research projects are now available for publication, along with several 2024 non-completed titles, which are updated monthly with new possibilities. For application-based projects, interface designs, and mini projects, you can also rely on NXFE for top-quality solutions. We provide exceptional PhD assistance with full publication support and offer an installment payment option, allowing you to pay module by module. Let NXFE guide you through your research journey with flexibility and expert support. Thank you.